How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at molecular shapes and polarity. So our objectives will be to, students will determine the polarity of molecules based on their shapes determined by the valence shell electron pair repulsion model. So a little review, electronegativity and bond polarity. So we know electronegativity is an atom's attraction to electrons in a bond. So the higher the electronegativity, the greater the attraction. Right, so if we go ahead. You can think of it as like it's how much they want to hog the electrons being shared, right? So I have two molecules here. One's H2 and one's HCl, right? So when we're talking about bond polarity, when electrons are unevenly shared between the two atoms, they create a polar bond. So you can see hydrogen, since they have the same electronegativity, they're going to form a non-polar bond. They're sharing that electron evenly. It goes around the right hydrogen once, goes around the left hydrogen once, and they just kind of evenly share it. Whereas if you take a look at HCl, chlorine has a much higher electronegativity than hydrogen. So you can see that that electron spending a lot more time around the chlorine than it does the hydrogen. That is what a polar bond is. It's unevenly shared. Now, since electrons hang around one of the atoms more than the other, this atom becomes slightly negative because electrons are negatively charged, which means the hydrogen, since it's almost losing that electron, right? It donated one of its electrons and chlorine's hogging it, would make it partially positive. So that's bond polarity. So let's talk about dipole moments. So a bond dipole is the measure of separation between the positive and negative charges in a bond, specifically a bond. Now these are vector quantities, and what that means is they have a magnitude and a direction, right? So speed is just, it doesn't matter what direction you're going in, that's the speed. But if you're talking about velocity or something, that's a vector quantity. It also implies what direction you're going. So a bond dipole is a vector quantity. It tells you how much the charge is separated, but also in which direction is it being separated. So you want to point an arrow towards the more electronegative atom, and the other one gets like a positive through it. It's like the feathers on an arrow. So because H2 is nonpolar, there is no bond dipole, right? But for HCl, you would draw an arrow going, hey, the electrons are being pulled in this direction. And then you would put a little, feathers on the arrow right there. So it looks like a plus sign. And that is your bond dipole. So dipole moments is a measure of the separation between positive and negative charges in a molecule specifically. So if I were to take a look at HCl, the bond dipole is the same as the dipole moment because it's just these two atoms. So the molecule is just those two atoms. It's the sum of all the bond dipoles in a molecule. If I take a look at the bottom one here, this is CCl4. It's going to be in a different situation than HCl. So now if all of these bond dipoles cancel each other out, then the dipole moment equals 0 and the molecule is nonpolar. So if I take a look at CCl4, I'm going to draw the Lewis structure for it real quick. We know chlorine is more electronegative than carbon. So what's happening is all of these chlorines are pulling electrons kind of away from that carbon atom. But because all of those chlorines are symmetrically placed around that carbon, the whole molecule is nonpolar. The bonds are polar, but it's like a tug of war, and they're evenly matched and in opposite directions. So overall, there is no like North Pole or South Pole. So if they don't cancel out, then you have a polar molecule. So CO2 is an example here. So we know oxygen is the more electronegative atom than carbon. So we have these bond dipoles in light blue. But what about the whole molecule? Is the whole molecule polar? And the answer to that would be no, because when you add these bond dipoles together, they cancel each other out. It's like a tug of war where they're evenly matched and in opposite directions. So overall, nobody's going anywhere, right? So that would make the molecule non-polar. Even though there's polar bonds, the whole molecule is non-polar. So if we take a look at the electrostatic potential of this molecule, you can see there's no, positive or negative pole or north and south pole like on a magnet. So we call this non-polar, right? There is a region where it's slightly more negative and slightly more positive, but it's not polar. There's no like north pole, south pole, positive pole, negative pole. H2O, different situation. right? So if we take a look, oxygen, being the more electronegative, is pulling the electrons towards it. Now, these bond dipoles in black, when you add them together, remember they're vector quantities, so it's not only the magnitude, but also the direction. When you add them together, kind of tip to tail, you can see there is an overall dipole moment for that molecule, which would make it a polar molecule. And that dipole moment represents where overall the electrons are being pulled. Right? So the electrons are overall being pulled towards that oxygen atom. So if we take a look at the electrostatic potential, you can see there is a negative pole and a positive pole. So that would make the water molecule polar. There's like a north and south pole, a positive and a negative pole. Right? And that would be the dipole moment for that molecule. So try these one out. Figure out, is it polar? Is it a non-polar molecule? Right? So pause it, draw Lewis structures or something, figure out what shape they are, and figure out if they're polar or not. All right, welcome back. CCl4 kind of cheated and went over this one earlier. So even though we have bond dipoles, they're all canceling each other out. Now, I know I'm drawing a two-dimensional shape for a three-dimensional actual geometry, but it still applies because we can tell that everything's going to be symmetrical around that carbon, canceling each other out, which would make CCl4 nonpolar. BF3, same deal. This one, the Lewis structure actually represents what the molecule actually looks like because it's a trigonal planar. And we go, all right, well, all of these bond dipoles are symmetrically placed around that boron, which means they're going to cancel each other out. So BF3 would also be nonpolar. Now, CH3Cl, well, let's see. I got CHCl. Well, hey, wait a minute. I know chlorine is the most electronegative there. And if I recall correctly, carbon's more electronegative than hydrogen. Overall, hey, wait a minute. These aren't canceling each other out perfectly, which means CH3Cl would be a polar molecule. If I take a look at BrF5, put Br 1, 2, 3, 4, 5, and then complete the octets brings me to 40, but I really need 42, so there's an unshared pair of electrons around bromine. Oh, hey, this unshared pair of electrons is really messing up that symmetry. So BrF5 would also be a polar molecule. So here's a 2D trick. Right, so if you draw the Lewis structures for all these, which is definitely the easiest thing to do compared to like building a molecule with a model kit or something, the trick you can use is look at the lines of symmetry for how you can draw it. Now, if you can draw more than one line of symmetry around that molecule or through that molecule, it's going to be nonpolar. So more than one line of symmetry means it's nonpolar. So let's take a look. All right, so I'm finishing up these Lewis structures. I might even change my pen ink so that we can see it better. Now, CCl4, well, here's a line of symmetry. Here's another line of symmetry. I could also draw them diagonally, so I got, more than one line of symmetry. That tells me that it's a nonpolar molecule. BF3, well, I can draw a line of symmetry this way, and this way. So I got more than one, which tells me that it's a nonpolar molecule. CH3Cl, there's only one line of symmetry in that Lewis structure. So that tells me that it's a polar molecule. And then same thing with BrF5. It's kind of harder to see because of how many things there are, but there's only one line of symmetry there, which tells me that it's a polar molecule. There's only one. All right, so summarize. Can you determine the polarity of molecules based on their shapes determined by the valence shell electron pair repulsion model? I hope so. If not, I've failed you. Okay, bye.